In this video, I'm going to show you my solution of class test 1, and I'll go over the main points with you. In question number 1, I wanted to see that you could write down working definitions of various things in symbols. A real number x is said to be rational, provided there exist integers m and n, such that x can be written in the form m divided by n. An integer x is said to be odd, provided there exists an integer k, such that x is equal to 2k plus 1. And if x and y are integers, we say that x divides y, provided there exists an integer k, such that y is equal to k times x. In question number 2, I defined for you a new working definition. I said that a function is said to be strictly decreasing, provided for all pairs of real numbers x and y. If x is less than y, then f of x is bigger than f of y. Suppose you were given some function and you wanted to prove that it was strictly decreasing. How would you do it if you used the method of contraposition? So you would leave this part of the statement alone, and then you would prove the contrapositive of this. This is P implies Q, so the contrapositive is not Q implies not P. And a common mistake that students made is that when they took the negation of this thing here, they wrote it as less than, whereas they should have written it as less than or equal to. So the proof would run like this. Let x and y be real numbers. Suppose f of x is less than or equal to f of y, and then you'd have a sequence of logical steps, and you'd ultimately try to deduce that x is bigger than or equal to y. So you'd have some point in the proof where you'd say, therefore x is bigger than or equal to y, and that would be the end of the proof. If, on the other hand, you were using proof by contradiction, you would assume the negation of this, and you would try to get a contradiction from that. The negation of this is there exist real numbers x and y such that x is less than y and f of x is less than or equal to f of y. And so the proof would be, suppose there exist real numbers x and y such that x is less than y and f of x is less than or equal to f of y. You'd then have a sequence of logical steps, and you would hopefully obtain some kind of a contradiction, and once you do, you would be able to say that the proof is complete. Now let's look at number 3. In number 3, I define a certain sequence of numbers. A sub n is defined to be 0 if n is even, and it's defined to be 10 if n is odd. And I gave you this statement here to prove about that sequence a sub n. And so what I wanted to know is, given a sequence of symbols like this, assuming that you want to prove that it's true, do you know how to respond in the appropriate way when you see each of these little pieces? Okay, so there are 3 pieces for you to deal with. So in your proof, when you see this, you're supposed to say, let capital N be a natural number. And when you see this, you're supposed to choose little n in some appropriate way so that this part of the statement will automatically be true. The choice of this little n is somehow going to depend upon the capital N that was given to you in the first step. The key point is that you have no control over what that capital N is. You don't know if it's 20, you don't know if it's 1, you don't know if it's a million, and so you have to take that into account. Your choice of little n has to work no matter what the capital N was given to you. So since you want your a sub n to be bigger than 5, you'd better choose your little n to be odd. Otherwise you'll get a 0 and that isn't bigger than 5. But you also have to guarantee that your little n is bigger than the capital N that was given to you. And since you don't know what that capital N is, you can't say something like choose little n to be 11, or any specific number that's odd. Okay, the fact that it's odd will force this to be true, but it won't force this to be true. So the way around that is to say, choose little n to be any natural number that's bigger than the given capital N and is also odd. If you do that, then this will be true automatically, and this will be true as well. Okay, so there you see how I've written out the proof. Now, for just for interest's sake, can you figure out what is really being expressed by this in terms of the original sequence? What it's actually saying is that we have a sequence A sub n with the property that there are infinitely many terms in the sequence which are bigger than 5. Because it's saying that no matter how far out you go in the sequence, you can always find something else in the sequence farther out still where an is bigger than 5. And this is related to something you'll study later called the lim sup of the sequence, LIMSUP. But that's something that you'll come to much later. Now finally, we have here what is the working definition of this limit statement here. I gave you the opportunity on the next page to write down a formal proof of this statement. And so we'll talk about that more on the next page.